Welcome, guys. This video is going to cover nuclear energy. This is the last of the Chapter 15 lecture that we started in class, so let's just dive right in. How does a nuclear reactor work? Essentially, we're using nuclear fission, so that means we're splitting things in reactors. That process is very inefficient. We're going to lose lots of heat in the process. You see our fuel here is uranium ore packed as pellets. We process and put them in fuel rods and into fuel assemblies, and then the control rods absorb the neutrons or the kind of the waste. Typically we use water as a coolant because, like I said, it is a very inefficient process. We're going to lose a lot of heat, so that's has to go somewhere. Typically we use water to absorb the heat. We some more vocab. We have what's called a containment shell around the core, just in case there's a meltdown. And then the water is going to have to go somewhere. So are we going to have water-filled pools? What are we going to do with these spent fuel rods? Are we going to bury them in pools? Are we going to bury them in a mountain? What's going on with that? Here's a diagram. Can't really see it. Here's a more zoomed in version of the same diagram. Again, basically, we see our fuel on the left side. We got our coolant. We got a heat exchanger that's turning our turbine. So we need the heat for the steam so that we can turn our turbine and generate electricity. And then all the rest of this is essentially cooling off the water that we're heating to turn the turbine. Just like we talked yesterday, everything is about turning a turbine. How can you get that turbine to turn? In this case, our fuel source is a nuclear reaction. This picture demonstrates how fission works. Notice that it is a cascade. We split one atom, and that causes more atoms to split, which causes more atoms to split, which causes more atoms to split. So it's a chain reaction. So it's going to allow us to release a huge amount of energy rather quickly and with as little input as possible. Again, we're going to lose a lot of heat in this process. It's not efficient, but we are releasing large amounts of energy. So what does it take? Basically, what's the life cycle of nuclear fuel? Well, we got to get the uranium. We got to get the fuel source. Once we mine the uranium, we got to process it. We got to put it in the fuel rods. We got to enrich it. Then we're going to have to use it. We're going to have to store the waste. And eventually we're going to have to decommission the reactor. What do we do with it then? When we're done with a nuclear reactor, what do we do? Can we just let it sit there and break down over time? Or do we have to build some sort of a dome over the reactor so that it doesn't leak? Zoom in a little bit more here. So that's what this is trying to demonstrate. So we're going to have to mine the uranium. We're going to have to process it. Then we're going to put the fuel assemblies in the reactor. We're going to use the reactor. We're going to have to decommission the reactor, store the fuel rods somewhere, and then usually we end up burying our radioactive waste somewhere. We can recycle some stuff, but there are lots of people, my Biology 1 students in particular, are really bad about thinking that nuclear energy is renewable. It's not. It's just a longer time span that we're talking about being able to use it. It's still a non-renewable resource. There's still a limited amount of uranium on the planet, so it's still a non-renewable source. So when my parents were kids, it seemed like nuclear power was going to take over, and it was the rage. And I can remember learning about nuclear power and still thinking it was probably what was coming, but it never blew up like we thought it would. Notice on the slide here it says it's the slowest growing energy source and it's expected to decline. Why is that? It's expensive. Poor management, that refers to the management of the research as well as the management of the overall nuclear program. Low net sorry, let me try that again. Low net energy yield for the nuclear fuel cycle. There's of course safety concerns. We have meltdowns. People freak out about nuclear radiation, things like that. Since it does have such a low net yield, we need government subsidies, and spending fluctuates. Sometimes we can't afford to spend money on nuclear energy, sometimes we can't. And then, of course, concerns of transporting uranium. What are we going to do with the waste? What are we going to do with the waste, and how are we going to get it to the disposal site? How do we make sure that the train that we're shipping the uranium fuel rods on doesn't derail? How do we make sure that the truck that's hauling it doesn't get into an accident? Things along those lines. So what you're looking at is potential energy capacity of these plants. So it seems like they could be, theoretically, they could be really good. We have the potential to generate a ton of power, but we aren't maximizing our potential at the moment. Here are nuclear power plants that are still around today. Notice we don't have any here in Indiana. There was, in the 80s, there was a nuclear power plant that was in the process of being developed, but it never worked out. Never ended up coming to fruition. So we do have nuclear power plants, just not a lot of them. So anytime you talk nuclear, you have to talk about Chernobyl. April 26, 1986, we get in Chernobyl, Ukraine, there was a meltdown. A series of explosions caused the roof of the reactor building to blow off. Not good. Partial meltdown and fire for 10 days. 350 people in the city of Pripyat had to evacuate. A whole city had to evacuate. Crazy. Huge radioactive cloud spread over many countries and eventually the world. Tainted the water supply, tainted the air supply, messed with agriculture. We can take soil samples from before 1986 and we don't see uranium. We take soil samples after 1986 and they all have samples of uranium. The radiation covered the globe. So that's why accidents are a concern. It's not just a local accident where the local ecosystem is going to be messed up or maybe a few people are going to be impacted. The whole world is going to be impacted if we have an accident here. So when we talked risk, we talked about the fact that humans don't do a good job of evaluating risk. Well, this is a pretty decent risk. The potential, if that risk were to occur, is really high here. So, like always, we need to look at our advantages and disadvantages. We've kind of talked about all these, so I'm not sure we need to spend much more time on them. Okay, so I sort of have talked about this, but here's a little bit more detail. What do we do with spent fuel rods? We talked about the fact that this is not a renewable resource. We have to replace the rods every 3 or 4 years. We've got to cool them down in water-filled pools usually. Then we'll put them in a dry cask and we have to store them for thousands of years. Of course that's going to be vulnerable to a terrorist attack. If I'm trying to impact as many people as possible, I'm going to look for those spent fuel rods and that's where I'm going to focus. So it's something that we don't have a lot of control over once we're done. Yes, we can secure the area, we can secure the mountain that they're buried in, whatever that may be, but that's a potential risk we have to control. So check this out. Dealing with radioactive waste produced by nuclear power is pretty difficult because we have to store it for 10,000 to 240,000 years. 240,000 years is a long time. A lot's going to change between now and 240,000 years from now. So how do we keep it safe in that amount of time? Seems like we would just bury it as deep as we possibly can. We don't have to worry about somebody stumbling across it. We don't have to worry about a tornado hitting it. Maybe an earthquake's an issue. Should stay buried for 240,000 years unless there's some sort of earthquake, something like that. We still don't have a facility to store spent fuel rods. Some people say maybe we should shoot it into space. What happens if that finds the sun? What happens if that finds other radioactive sources? It's just too dangerous. So what do we do? 1985, there were plans in the U.S. to build this facility we've been talking about in Nevada. It's going to cost $96 billion. And essentially, that was going to be our one storage spot for the whole country. So there were going to be a lot of shipments coming in. The downside to using Nevada is the rock is prone to fractures. We're in an earthquake zone, so those two things don't go well with something that's potentially radioactive. And again, it decreases national security. So make sure you check out that case study in your book. Your book talks about it in a lot more detail. But what do we do with the old plants, the whole plant itself? Well, we got three options there, as you can see on the screen. We can tear it apart and and store the radioactive materials, like we were talking in Nevada. You could build a dome over it. That's kind of enclose the plant in a tomb, monitor it for thousands of years to make sure nobody breaks in, basically that nobody breaks in, that it's safe. And then enclose the plant behind a physical barrier for full-time security until a storage facility has been built. That's basically turn it into a military base and make sure that it's guarded 24/7. Really similar to number 3, but we're in the process, in 2, we're in the process of destroying it for good. Number 3, we're just leaving it there until it breaks down on its own. So can we reduce our dependence on foreign oil, and can we reduce global warming? Maybe. There's no carbon dioxide emission in the plant itself, but enriching the uranium and transporting the uranium, there's a lot of CO2 involved in the fuel cycle, so in processing it and getting it ready and using it and disposing it and so on. There certainly are nuclear power advocates. Make sure you see this 2007 stuff about Oxford in your book. It seems like, again, the answer is maybe. Maybe it'll reduce the impact of global warming and climate change. For our society, we've decided that the risks are too great, so we're not encouraging and increasing our use of nuclear reactions. So there's a theoretical thing out there about nuclear fusion. Seems like if we can split atoms, we should be able to fuse atoms together. Notice we've been in the research phase for 50 years. We spent $34 billion on this, and we really haven't gotten anywhere. In 2006, there was an agreement to build a large-scale nuclear fusion reactor by 2018. The update on that is that they have just started planning. So they're still way off on this goal. We're still 5-10 years from having a nuclear fusion reactor. If we could, theoretically, that would be a great renewable energy source. So we're kind of at a crossroads with nuclear power. Some people that like nuclear power say we need to fund the research. We just need to do it better. It's a good idea, but we're not there yet. Opponents say it is a good idea, we're not there yet, so let's devote the money to solar and wind and hydropower and develop safer alternative energy sources that are renewable. So it's kind of hard to tell what the future of nuclear power is going to be. Certainly a lot of potential, but definitely we're not there yet on it.